Hello, my name is Noam Zilberstein. I work in the Facebook Programming Languages and Runtimes group, and today I'm going to talk about my experience eliminating bugs with dependent Haskell. Modern software is becoming increasingly large in both scale and complexity, to the point that we can no longer reason about correctness using standard software engineering techniques. Those within the Haskell community have been experimenting with dependent types for a long time. But critics of those techniques say that they're too complicated and not practical for use in the real world. Today, I'm going to talk about my experience using dependent types in real-world production systems, and the types of bugs that I was able to eliminate as a result. This work proves that dependent types are, in fact, practical for use in the real world. At Facebook, Haskell is used to write abuse detection rules as part of a system called Sigma. Sigma rules help prevent a wide variety of abuse types, including spam, fake accounts, and fraud. Due to the adversarial nature of abuse detection, Sigma rules often need to be deployed to production very quickly. This means that Sigma developers sometimes have very little time to test their code, creating an even stronger need for compile time correctness guarantees. Sigma is also a very large-scale system as it's invoked on nearly every interaction that a user has on Facebook, or millions of times per second. The goal of programming with dependent types is to express more invariants at the type level. Haskell has a very expressive type system, but it's still not a fully dependently typed language. This means that there is a phase separation between terms and types. The downside of this limitation is that we cannot express everything at the type level, and that we need additional structures such as singletons in order to connect types to their runtime values. However, the upside is that Haskell has a more powerful type inference system than many dependently typed languages such as Agda. In practice, this means that GHC's constraint solver can automate more of the invariant checking than a true dependently typed language would be able to do. An interesting result that I came across is that using more expressive types often guides the programmer's thinking towards writing more correct code, even if we're not proving every invariant about the code. We'll see some examples of this soon. Now, let's look at how dependent types are used in production at Facebook. The Thrift Interface Description Language is used so that developers can define data structures and remote procedure calls to use across programming languages. This would allow a developer to create a service in C++ and then query it from any language that they want. The Thrift compiler translates Thrift code into native code in some programming language like Haskell. Sigma rules make extensive use of Thrift code in order to fetch additional data that they need to make decisions about content. The correctness of this code is crucial. Any bugs in the Thrift compiler could cause abuse detection rules to behave in an unexpected way. On the left, you can see an example of some standard Thrift code, and on the right, you can see the result of running the Thrift compiler on this code to generate Haskell code. The first line is a definition of a type alias. We're creating a type called ID, which is a 64-bit integer. The next item is a struct holding information about a user. This is very similar to a struct in C. In Haskell, we translate this to a record type. The third item is an enum, which can be one of two values, either dog or cat. In Haskell, we emit a standard sum type for this. And finally, the last item is a service, which defines a remote procedure call for getting information about a user. In Haskell, we emit an IO function, which would be used to query this service, and we return information about the user. The Haskell Thrift compiler makes extensive use of dependent types and its internals in order to express correctness invariants about the code. By contrast, the C++ Thrift compiler, which is used to compile Thrift for other languages, does not use dependent types. The C++ implementation had many more bugs than the Haskell implementation, including infinite loops, accepting inputs that are ill-typed, and ambiguous behavior. Let's start by discussing the design of the abstract syntax tree for the Haskell Thrift compiler. On the right, you can see a potential implementation of the representation of a Thrift type within the compiler. We have three base types, ints, bools, and strings. We have two collection types, lists and maps. And then we have a named type, which could be either an enum or a struct or a type alias. While this implementation certainly gets the job done, it is not very expressive. In particular, it doesn't tell us anything about whether the type we're looking at is well formed. It doesn't tell us what a valid value of a given type should look like. And we don't even know if some named type is a struct, an enum, a type alias, or it may not even exist at all. We'll start by extending the AST in order to guarantee that a resolved type is well formed. The first step is that we need to be able to distinguish between a resolved type and an unresolved type. For this, we use a data kind. You'll notice that the status data type is just a standard Haskell data type with two values, resolved or unresolved. The data kinds language extension allows us to lift status to be a kind, where tick resolved and tick unresolved are both types of kind status. We also convert type to be a generalized algebraic data type, or GADIT. This allows us to tell GHC that some of the data constructors can only be used in a resolved or unresolved AST. You can now see that the t-named data constructor is only valid in an unresolved AST, whereas t-alias, t-struct, and t-enum can only be used in a resolved AST. This guarantees that after type checking, all named types must be converted to a more concrete type. By contrast, the base types and collections are not constrained to be resolved or unresolved because they can appear in either AST type. We could have implemented this using two completely distinct ASTs. However, that would have resulted in a lot more code. Using the GADIT and DataKind approach, we're able to write generic functions that work on both resolved and unresolved AST types. An example is a pretty printer. The thrift code on the right is invalid because it defines three type aliases in terms of each other. When faced with this input, the C++ thrift compiler went into an infinite loop. This issue was quite hard to debug because thrift compilation often happens as part of a large multi-process build job. Therefore, the developers did not know why their build job was hanging. A correct implementation of thrift compilation would require a topological sort of type aliases in order to detect cycles. When implementing the Haskell thrift compiler, the need for topological sort was implied by the requirement that resolved types need to be deeply resolved. More specifically, we were not able to construct a type unless all of its dependencies were already type checked. The C++ version only shallowly resolved types, which is what led to this bug. GADITs and data kinds can also be applied in a variety of other use cases outside of compilers. One example is to describe different types of abuse detection rules in Sigma. Sigma rules execute in two rounds. When a user goes to facebook.com, the request goes into a cloud where it finds a Facebook web server. The Facebook web server will then call into Sigma in order to determine if the request is abusive. First, Sigma will run a variety of synchronous rules. These rules can actually affect the web request itself. For example, they could apply additional metadata to the request before it gets back to the user. After the synchronous rules finish, the Facebook web server will render the page in the user's browser. After that point, Sigma runs some more expensive classification in the async round. These rules cannot affect the outcome of the request, but they can do some actions such as logging. The key invariant that we want to uphold in Sigma rules is that synchronous actions cannot be returned in asynchronous rules, because the request that they're trying to modify has already completed. In order to achieve this, we model the Sigma response type as a GADIT, where the tag constructor is limited to only be synchronous, but the log constructor can occur in any round. Using this scheme, the code on the right is ill-typed, because it's attempting to return tag in a rule that should be async. Before we introduce this type level distinction, the only way to determine if a given rule was sync or async was to look in some separate configuration file. It became intractable to know whether the code you were dealing with was synchronous or asynchronous, especially in deeply nested helper functions which may be shared by both synchronous and asynchronous code. Introducing this type-level distinction uncovered hundreds of bugs where we were silently dropping synchronous responses. Now back to Thrift. In addition to being able to tell if a type is well-formed, we also want to be able to tell if a value of that type is well-formed. In order to achieve this, we add a second type parameter to the type gadget, which tells us what Haskell type we will use to represent valid literals of that type. For example, Thrift integers, booleans, and strings will be represented as Haskell integers, booleans, and strings. Now we're ready to define our main type checking function. On the left, you can see the representations of both untyped and typed constants, where untyped constants don't have any type parameter, but typed constants do. So a typed constant of type integer can be a literal integer. The type checking function now associates the type parameter from the type and the typed constant. By doing this, GHC actually guarantees that the type checked constants are well formed. You can see that the first two lines of the type check function are correct and valid Haskell. So we pattern match on the tint constructor, telling us that we need to output an integer. The intlit data constructor carries an integer, therefore we're able to return it, no problem. The string case is very similar. However, the third case is incorrect, and luckily it's also ill-typed in Haskell. We cannot return a string when we pattern match on the tint data constructor. It's worth noting that despite the expressive type signature, the typed const function can still go wrong in several ways. For example, you could always return 0 for any tint, or you could always produce a type error on any input. However, in my experience, those mistakes aren't particularly easy to make because they involve knowingly doing something which is incorrect. This idea of associating type parameters within a function signature is useful in a wide variety of use cases outside of compilers. In Sigma, we fetch data using a framework called Haskell, which automatically parallelizes data fetches and caches the results. Data fetch requests are represented as a gadget, where each request declares what its return type will be. This allows us to have type-safe data fetching and cache lookups. On the right, you can see a request type which defines two data fetches for getting the name and pet of a user, where the name request returns a string and the pet returns a pet. The data fetch and cache lookup functions use the declared return type of the request as their own return type. The cache insert function is a little different. It takes a value with the return type of the request and just inserts it into the cache. You can now see how we can define a wrapper for getName, which uses data fetch under the hood to type safely fetch the data. So this idea of associating type parameters in a function works very well in a variety of use cases. However, it doesn't help us very much in Thrift when we need to describe what a well-formed struct or enum looks like. Structs and enums are user-defined types, meaning that we don't have a representation for them in Haskell that we can use. However, using a variety of type-level constructs, we can dynamically create representations of these types. A well-formed struct must have well-formed values in all of its named fields. We can represent this as a type-level list of type-level strings and types. In Haskell, symbol is the kind of a type-level string, and star is the kind of a regular value type. Because Haskell is not a truly dependently typed language, we need some way in order to retrieve the value of type-level strings at runtime. The known symbol type class allows us to do this. On the right, you can see the definition of struct schemas and struct values. A schema is either empty or it's a named field const onto another schema. The gadget allows us to reflect the type level representation of the field's name and type to the type level. We can then associate that with the struct value, which has a very similar structure to a schema, except that it also has a typed const, which is the value of that field. Now, the function to type check a struct associates the type parameter from the schema and the struct val, which will guarantee that the output struct val is well formed. We can now incorporate this into the definition of typed const, where we simply wrap the returned result as a literal. On the right, you can see an example of what the schema for the user type that we examined earlier in the talk would look like. Note that the strings you're seeing here are type level strings, not term level strings, and we are applying them to the sconst constructor using a visible type application. Enums are almost the opposite of structs, in that instead of all fields needing to be present, enums just require that one field is present. In this case, the schema kind is just a list of symbols. We don't need additional types of kind star. An enum value must contain a proof that the particular identifier of that enum is a member of the enum schema. A membership proof is basically a proof by induction. P here is the base case, which says that the element we're looking for is the head of the list. P there is the inductive step. It says, give me a proof that X is contained in some list, and I'll produce a proof that X is contained in that list with an additional element at its head. Now, the typecheck enum function can only succeed if we're able to build a membership proof for the given name and schema. We use a little bit of complicated machinery here. EQT checks that two type level strings are equal, and if so, it produces a proof that they're equal. In this case, you can see the proof is called refl, or reflexivity. We can now complete the typecheck const function by invoking the typecheck enum function and then wrapping the membership proof as an enum val. We can see an instance here of where we need to add a little bit of additional machinery in order to make up for the fact that Haskell is not a truly dependently typed language. We use the sum symbol val function in order to get the type level representation of a term level string. We can't directly pass a term level string as a type. It's worth noting as well that the act of creating a membership proof increases the time and space complexity of the code. Because the enum schema is represented as a type level list, we need linear time and space in order to construct and store the proof. We could reduce the complexity by using a different type level data structure, but in practice we found that performance was not an issue and it was not worth complicating the code in order to design a more performant type level data structure. Now let's get into some additional bugs that we uncovered due to our dependently typed code. The example on the right defines a thrift enum with 3 values. The first 2 constants are valid. You're allowed to reference an enum by either its name or its integer value. However, the third constant is not valid because X has no member with value 3. The C++ thrift type checker didn't really make any distinction between integers and enums, so it would have accepted this input. However, in Haskell, this bug would not have been possible because there would be no way to construct a membership proof for the third constant. Another bug that we found involved implicitly coercing values. The constant on the left appears to be defining an error state, but it's actually okay. The developer made this mistake because of subtly different capitalization between different enums. The C++ thrift compiler had no problem with this code, whereas the Haskell thrift compiler emitted a type error. In fact, it would have been impossible for the Haskell thrift compiler to accept this code because there would be no way to construct a proper membership proof. Real production bugs of this nature were found because of the Haskell thrift compiler. In Thrift, symbols from other modules must be qualified by the module name, and enums can optionally be qualified by the name of their type. In this example, we define a constant called dog with value animal.dog. However, it's ambiguous whether this value is referring to the dog constructor from animal or the dog value from the animal.thrift file. We don't know if the value is 0 or 1, 2, 3, 4, 5. The C++ Thrift compiler arbitrarily resolved this ambiguity, which led to unexpected behavior in production. There are a variety of reasons why this could not have happened in the Haskell Thrift compiler, including smarter name resolution and more strict type checking. We would not allow you to use an enum constructor for an int32. We have additional uses for type-level schemas in Sigma code. Sigma rules receive input as untyped JSON maps. Input lookups can fail at runtime in one of two ways. Either the key that the developer is looking for may not be present, or the key may be present but with the wrong type. Lookup failures are very prominent in production. In fact, they make up about 50% of all rule failures. Strongly typed inputs are also difficult because of code sharing. Many rules which take different inputs need to be able to share common helper functions, which take some subset of the inputs of all of the rules that use them. In order to support input lookups in a type-safe way, we encode the schema of the function as a constraint. This makes code sharing easy. Each rule has its own strongly typed input, but by implementing the has type class for all the input keys, we can overlay a schema on top of this strongly typed input, which allows us to share code. Note that the type-safe lookup API is pure because it cannot fail at runtime. Input lookups now work using visible type applications of type-level strings instead of standard applications of term-level strings. This is a pretty foreign concept to most Sigma developers who are not well versed in advanced Haskell features. However, we found that the syntax is quite simple to use because it looks much like a regular string application. You don't really have to think about the fact that it's a type or a term. Today, I've shown examples of how dependent types have been successfully used to eliminate bugs in production code. I hope that my work will inspire other Haskell programmers to use dependent types in their own software projects. Modern software is only becoming more complicated and larger in scale, creating a need for even stronger correctness guarantees at compile time. The software industry is already moving to a place where more and more code is statically typed. This includes initiatives to build type checkers for languages like Python and JavaScript that are traditionally dynamically typed. My work provides proof that it's not only worthwhile to statically type check code, but also to increase the expressiveness of modern languages. Thank you for listening to my talk.